Hi everyone, in today's presentation we will be covering chapter 4.1, Visualizing Fractions from the OpenStax Pre-Algebra textbook. There are quite a few learning objectives in this particular video, but the core objective really is to understand the meaning of fractions and then look at the differences between different types of fractions, improper fractions and mixed fractions, be able to convert between the two, then also look at equivalent fractions. What is the meaning of equivalent fraction? How to model it, how to find it, and then also to locate fractions on the number line and order those fractions. Okay, so those are the core learning objectives that you'll find in this textbook chapter. Okay, but I want to start with this first introduction question that I have on the screen here, which is to define what is a fraction, and then how would you display a fraction on the following number line. So I'd go ahead and pause the video here and see if you can answer these two questions to start. All right, so let's go ahead and define what a fraction actually is then here. So a fraction is a part of a whole. For example, on the screen here, we have a circle that is divided into different divisions here. The division then is of thirds, right? That's the bottom number, called a denominator, and then it moves up as you increase the number of slices you have. So 1/3, 2/3, 3/3, so on and so forth. Okay. Now a fraction, if I look at a very specific scenario of when to use a fraction, it would be like with money, for example. So partial parts of a dollar, half a dollar, 50 cents, 25 cents of a dollar, 75 cents of a dollar. These are fractional elements of the dollar, right? In this case, $1 is over 100, right? 100 pennies essentially makes a dollar, okay? Now, if I look at a fraction on a number line, then a fraction is the in between the whole numbers, right? So from 0 to 1, we have a half. From 6 to 7, you have 6.5. So the number line itself are these whole numbers, but these fractions then would come in between parts of it. Now, if I were to recognize a fraction, these two sentences kind of describe what we're talking about. So for example, on the left-hand side of the screen, we have a pizza. And the first question is, how many slices do I have left to eat here? So we see that we have 2 slices left to eat. And then the other question, how many slices was the pizza cut into at the beginning? And we would say, well, 5, right? So 2 and 5. Now, I could write these sentences all the time. I wouldn't necessarily need a fraction to show it, but you might see the problem there. If I'm always having to write out these sentences, that's not efficient. The time would take a bunch of time, or take a while, I should say. And then if I was trying to like combine different numbers together, it would become kind of convoluted, right? There'd be a lot of words and numbers on the page or whatnot. So fractions, or structuring this exact scenario as a fraction, makes things smaller and more efficient. So we could write this then, how many slices do I have left to eat? How many slices was the pizza cut into at the beginning? Simply as a fraction that you see on the screen here, right? 2/5 of a fraction. You put a number on top, a fraction bar, and then a number on bottom. Now, each of these different numbers, the top number and the bottom number, have a particular definition tied to it then. So the top number is a numerator. A numerator then in a fraction shows how many parts of the whole you have. The bottom number is a denominator. So a denominator is the bottom number in a fraction that shows how many equal parts the whole is divided into, right? So 2/5 of a fraction. The first couple questions here then for recognizing fractions ask to define a fraction that you see shaded red below. So this first fraction we see here, we can see that the denominator, what the divisions are 4 in total, right? So this is divided into fourths. Then we see that we have 3 of these different slices actually shaded in. So we would say this is a 3/4 fraction here. Now, question 2, the shape's a little interesting, a little different. The principle or process is the same. As we first decide, okay, what is this shape divided into? What's the denominator here? So To figure this one out, we need to count from 0 to 1 in all these little increments here. So if I was to count, we have 1, 2, 3, 4, 5, 6, 7 in total. So this would be the denominator here, 7. Now to figure out the numerator, we're going to count how many of the slices we actually have. So I'm actually going to fill in the rest of the number line here. So this is going to be 1/7 of a fraction. This is going to be 2/7 of a fraction, 3/7 of a fraction, 4/7 of a fraction, so that's our answer, 5/7, 6/7, and then ultimately 1 can be written as 7/7. So remember, fractions are division, so 7 divided by 7 is 1. Our answer, though, in this case, is going to be 4/7. All right, let's look at question number 3 now. So question number 3 is interesting in that there are 2 shapes here. So this first one is filled in as a full whole. Now, if I was to represent this as a fraction, this would be represented as 4/4. That's the first shape. And then you have the second shape, which you're basically combining or adding to the first shape. So this is going to be 3/4. Now, when you combine fractions or add them, you are adding the top number, the numerator, which is 7, and then you're keeping the denominator the same, which is 4. Now, I commonly see a mistake made in that we add the denominator and then it would be 7/8, and that would be incorrect. Now, there is another way of writing this instead of as 7/4. What if instead of 4/4 you wrote this as 1? You could totally do that, and then you have the fraction next to it, and this would be 3/4. So this and this are equivalent ways of showing that particular fraction, and they have specific titles to it. I'll save that for another slide. So we're going to come and we're going to actually look at what these 2 fractions are defined as and how to convert in between them. So one way to understand fraction equivalencies is with fraction tiles. So at the top here you have a 1, a whole, and then under each of these you have equivalent fractions or fractions tiles that build up to that 1. So for example, if I have the question, how many 1/2 tiles does it take to make 1 whole tile? You would say 2, right? How many 1/4 tiles does it make to make 1 whole tile? You would say 4. How many 1/8 tiles does it take to make 1 whole tile? You would say 8 here. So 2 tiles, 2/2 equals 1, 4 tiles, 4/4 equals 1, and 8 tiles, 8/8 also equals 1. Core learning point here is that if you were trying to build up to 1 and you're looking directly at the denominator here, the denominator tells you how many tiles you need to then equal 1. Okay? Next, we have the 3 different types of fractions. So, looking at the screen here, do you know what each fraction is called? 1/3, 4/3, and 1 1/3. So to start, 1/3 is what's considered to be a proper fraction. A proper fraction is a fraction that is less than 1, So in this case, we have 1 as the numerator, which is smaller than the 3 that's in the denominator. Next, we have an improper fraction. So an improper fraction then means it's more than 1. So the numerator is then bigger or equal to the denominator, which is smaller or equal. So I could have 4/3 as a fraction. That's an improper fraction. You could also have another improper fraction. Let's say you wanted to structure something that's in thirds, but you only have 3 slices of that, so 3/3. That is an improper fraction, which also equals 1. So 1 is the whole number form. 3/3 then is the improper fraction form. Finally, you have the mixed fraction form. A mixed fraction then is a whole number, 1, and you can see kind of the circle filled in 1 here, next to a proper fraction, 1/3. So if I kind of flip back and forth between an improper fraction and a mixed fraction, you can see that they're essentially the same overall value here, right? The only difference is the Improper fraction, the one that's an overall whole, is sliced in with actual divisions. It's like if you get a pizza and you actually put the slices in that pizza, while the whole number here is just an overall whole with no divisions in between it. Now, what this tells us is we can convert between improper fractions to mixed fractions. Now, there are several ways to kind of think about this. I think one of the best ways to think about it, initially at least, is by using long division. So a long division model to help you figure this out. So let's go ahead and apply the long division model to this question, or this fraction 4/3, and we're converting to a mixed fraction. So what you will do is you're going to take the denominator 3, and that goes on the outside of a long division bar, while the numerator 4 goes on the inside. So 3 goes into 4 one time. You then multiply the answer in the quotient by your denominator, 3. So 1 times 3 is 3. 4 minus 3 is then 1. Now notice there are no more numbers after the number 4, so 1 is a remainder. The remainder becomes the new numerator of your fraction. So we're going to put 1 in the numerator, and then we'll put 3 in the denominator. So your denominator stays the same. Now there are an occasion where you're able to simplify the fraction, so then your denominator might change at that point, but to first bring it up, you're going to have the same denominator here. So 4/3 is equivalent to 1 1/3. Let's try 2 more of these, and you can pause the video before you go on. So we have 7/4 and 12/8. So to start with 7/4, let's go ahead and take the denominator 4 and put on the outside of a long division bar and the number 7 on the inside. Then from here, we're going to ask how many times does 4 go into 7? Well, 4 goes into 7 again one time. 1 times 4 is 4, and 7 minus 4 is equal to 3. So 3 is a remainder. This becomes the new numerator of your fraction, and the denominator stays 4 here. Okay, so 7/4 changes to 1 3/4 here. Question 2 then is 12/8. We're going to take 8 in the denominator and put on the outside of a long division bar, and we're gonna put 12 on the inside here. So 8 goes into 12 one time as well. 1 times 8 is 8. 12 divided by 8 is then 4. 4 is a remainder. That becomes the new numerator of your fraction, while the number 8 becomes your denominator. So at this point, we're going to go ahead and divide. Oh, actually, before I get ahead of myself. So you have 1 4/8 here. Now, 1 4/8, you might notice that 4/8 can be simplified, right? There's a factor that goes into both numbers. Now, there's a factor of 2 that goes into both numbers, but 4 also can be divided by the number 4, right? And 8 can be divided by the number 4. So 4 is actually the biggest number that goes into both. So we're going to write this then as a half here. So rewriting my fraction now, we keep the whole number 1. And now we take our simplified fraction, which is a half. Okay. So 1 1/2 is another form of this fraction. Now let's look at how to convert mixed fractions to improper fractions. So again, several different ways of thinking about this problem. You can think about it visually, or you can think about it in terms of a process or an algorithm that I have over here. So this process, the step-by-step process that I'm going to introduce is the following. So step 1, you will multiply the whole number by the denominator. 2, add the answer from step 1 to the numerator. This becomes your new numerator. And then step 3, keep the same denominator. Okay, so let's put this process into practice here. So looking at our first fraction, we have 1 2/5 here. So Step 1 is to multiply the whole number 1, in this case, by the number 5. So we're going to do 1 times 5. And then we're going to add that to a number 2. So 1 times 5 is 5 plus 2, that's the adding the answer from step 1, is 7. So 7 is your new numerator. Step 3, keep the same denominator. 5 stays the same. So 1 2/5 changes to 7/5 here at the end. Question number 2 is 3 2/7 here. So we're first going to multiply 3 times 7, which is 21. And then we're going to add that to our numerator of 2. So 3 times 7 is 21. 21 plus 2 is equal to 23. So 23 is the new numerator. Our denominator stays the same. Keep the same denominator, so 7 stays the same here. So our answer to question 2 is 23/7. Question number 3 then is 5.5. So let's multiply our 5 times 2 here, which is 10. And then we're going to add that to the numerator of 1. So 5 times 2 is 10. 10 plus 1 is 11. So 11 is the numerator. You then keep the same denominator, which is 2. So 5.5 converts to 11/2 as an improper fraction. Next, we have equivalent fractions. So fractions are equivalent if they're equal or represent the same amount. So for example, equivalent fractions to 1/2 includes 2/4, 3/6, and 4/8. Notice the area is the same. The difference then is you've added an extra slice into each of the fractions that come after it. Now, how do we actually solve for equivalent fractions or do this with a calculation? So here we have a half, and we're trying to figure out what is the numerator of an equivalent fraction. By the way, we know it's equivalent because of the equal sign, and we have a number on top and 8 in the denominator. So again, we could do this visually. So for example, you might notice that, okay, I have an overall half here then, and if I was to fill in all the blanks for a shape that has a denominator of 8, and then we count the amount of slices we have, we see that we have 4, right? 1, 2, 3, 4. So that is one way to do it. The other way you could look at it is, okay, if I go from 2 to 8, what factor do I multiply 2 by to get to 8? Well, the factor we multiply by is a factor of 4. Now the principle is whatever I multiply on the bottom part of the fraction, I then would multiply on the top part of the fraction. So we would then do 1 times 4 on top. So 2 times 4 is 8, 1 times 4 is 4. So in other words, if I was to rewrite this, we would say 1/2 is equal to 4/8 of a fraction here. Another example of this is the following. So if I have 1/4 is equal to 2/x here, what we would do in this case is we say, okay, we have the numerator, 1 and 2, so I know I can multiply this by 2, right? 1 times 2 is 2, and then whatever I multiply on top, I multiply on bottom. So I have 4 times 2, which is equal to 8 here. So rewriting this, I would then have 1/4 equals 2/8 as my fraction on the side here. Finally, in this set at least, we have x/6 equals 1/2. Now this is a bit different than the previous ones because now I'm going, how it's structured, is a bigger number to a smaller number. So if I kept it in this kind of structure, this setup, you could think about, okay, what number do I divide by 6 to get to 2? And the number you divide by 6 to get to 2 is 3. So 6 divided by 3 is 2. Whatever I divide on bottom, I then divide on top as well. So I divide this by 3. And then you think, okay, what number do I divide by 3 to get to 1? And the number you divide by 3 to get to 1 is 3. So 3 divided by 3 is 1. 6 divided by 3 is 2. Now, there's another way you could do it. Because this is an equation, you can swap the sides of the fraction. So you could rewrite this as 1/2 equals blank over 6 here. And from this direction, you can then say, okay, I have a smaller number 2 into a bigger number 6, so I can multiply this by 3 and then multiply this by 3. So 2 times 3 is 6. 1 times 3 then is 3, right? So we have 1/2 is equal to 3 over 6 here. Now, a little challenge question here in terms of a word problem. Same type of process as an equivalent fraction, but it asks us what fraction has a numerator of 12 and is equivalent to 3 over 4. Now, the key word here is numerator, right? So that's important. Now, what I first would start though with is the fraction you're given. So 3/4 here. You actually do it in a different color. So 3/4. You were then asked to find an equivalent fraction that has a numerator of 12. So we would put 12 in the numerator here. And then we're looking for the missing number down here. Now, the place I see the most mistakes made with this type of question is instead of putting 12 in the numerator, we would put 12 in the denominator. So if you had structured this question like this, with 12 in the denominator, yes, you can find an equivalent fraction like this, but this is not what that particular question is asking, right? From here, we can follow the same process we've been looking at. So we say, okay, we have 3 and 12. So what number do I multiply by 3 to get to 12? That would be by 4. So I can multiply 3 times 4 to 12. And then for the bottom one, I have 4 times 4, which is equal to 16. So we now have 3/4 is equal to 12/16 here. Now let's go ahead and look at fractions on the number line here. So we have what fraction does the point represent? So our first step here is we need to figure out what our denominator is, what the increments are actually divided by. And to do this, we're looking from 0 to 1. So I'm going to first go ahead and count how many increments there are. So I'm counting 1, 2, 3, 4, 5, 6. So I know this is of increments of 6. That's going to be our denominator. So then filling in the number line here, we can start with 0 out of 6, 1/6, 2/6, which simplifies down to 1/3, 3 over 6, which simplifies to 1/2, 4/6, which simplifies to 2/3, 5/6, 6 over 6, which remember 6 divided by 6 is 1, 7 over 6, which simplifies, or I shouldn't say simplifies, converts to a mixed fraction, 1 and 1/6, 8/6, this does actually simplify. You could have 1 and 2/6, or it simplifies further to 1 and 1/3. And then we have 9 over 6, which is 1 and 3/6, or simplifies down to 1 and 1/2. So our answer in this case then could either be 4/6 or the simplified version of 2/3. Then we have this number line here. So again, our process is the same in that we're first going to calculate the denominator. So counting the increments, we have 1, 2, 3. Again, I'm looking between 0 and 1. I'm not looking between 0 and 2 to figure out the denominator here. So I know these are by thirds now, so I can go ahead and fill in the rest of the number line. So I have 0 over 3, 1 over 3, 2 over 3, 3 over 3, which is 1, 4 over 3, which can be converted to 1 and a third here, 5 over 3, which is 1 and 2/3, and then 6 over 3, which can be reduced down to 2. So our correct answer choice in this case is going to be 1/3 here. The final number line we're going to look at has a dot that's beyond 1, so it's bigger than 1 in this case. Our initial process, though, is the same in that we're first looking to define the denominator. To do this, we're looking between 0 and 1, and I see that I have 2 total increment movements. That means my denominator is 2 here. So then filling in the number line, I have 0 over 2, 1 over 2, 2 over 2, which divides down to 1, 3 over 2, which in mixed fraction form is 1 and a half, right? 2 goes into 3 one time. Denominator stays 2. And then we have 4 divided by 2. Now this simplifies down to a whole number, just a whole number 2. So 4 divided by 2 is 2. The next concept that we're going to have is we're going to take the number line now and think about ordering fractions on the number line. And I first want to start with the concept, though, of number opposites to understand negative and positive fractions. First, though, starting with negative and positive whole numbers, integers. So in this case, number opposites, as an example, is 7 and -7. So 7 units away from 0, has a direct reflection on the negative side of the number line. That'd be -7, which is also 7 units away from 0. Now, like whole numbers, fractions also have fraction opposites here. So we have 1 and 7/8 as a mixed fraction, or 15/8 as an improper fraction. That has a direct reflection then of -1 and 7/8 over here. Notice how 1 and 7/8 is close to 2, -1 and 7/8 is close to -2. So one of the skills you will then be asked is to identify and locate the following on a number line, fractions here. So starting with, and we're just approximating really, so starting with 1/4 and -1/4. Let's look at that partnership grouping here. So 1/4 and -1/4, these are proper fractions. This top number is smaller than the denominator. So we're looking between 0 and 1. Now halfway in between 0 and 1 can be found here, so that's a half. Now 1/4 is then halfway in between 0 and a half. So this is about right here on our number line. So 1/4, and then its direct reflection is going to be about right here. So -1/4. Next we go to 1 and 1/3 and -1 and 1/3. So this is found a little after the 1. It's further along than 1/4, but it's still not directly at a half here, right? So we have 1 and a third, and then its reflection on the other side of the number line found about right here. So -1 and a third. Then we have 5 over 2. That's an improper fraction. My recommendation when you're looking at an improper fraction is to convert them to a mixed fraction. So 5 over 2 converts to a mixed fraction of 2. So 2 goes into 5 2 times. 2 times 2 is 4. 5 minus 4 is 1. So our numerator is 1 and our denominator is 2. So 5 over 2 converts to a mixed fraction of 2 1/2. So 2 1/2 is then found halfway in between 2 and 3. So I have 2 1/2 here, and then I have -2 1/2 directly on the other side here. Now, a core thing that we're going to do next is ordering fractions by its value. So if I look at this problem, or this number line I should say, and I ask myself, what is the biggest fraction? We would of course say the number that's furthest to the right. 2 1/2 is the biggest fraction. And then if I was to say, okay, what's the smallest fraction of this? Well, that's going to be its direct reflection, -2 1/2. So core learning point, -2 1/2 is smaller than -1 and 1/3, which is also smaller than -1/4, which is a little weird when you first look at it, right? You might say, isn't negative 2.5 bigger than negative 1/4? Well, remember, numbers or fractions in this case, farther to the right on the number line are bigger in value. Numbers or fractions farther to the left, farther to the left are less in value. Okay, so as we kind of plot these different next set of questions on the number line, think about that relationship there. So next we have the following set of questions where we're asked to order each of the following pairs of numbers or fractions using a less than or greater than sign. So question 1, we're asked to find what's greater in value or less in value, negative 2/3 and negative 1. Question 2, negative 3/2 and negative 3. Question 3, negative 3/7, negative 3/8. Question 4, negative 2 and negative 16/9. So I would pause the video here, try to draw this out visually on a number line, and then see if you can look at the differences in values between them. So looking at question 1 then, we have negative 2/3 and negative 1. Now, negative 2/3 is greater than negative 1. And you can see this visually represented on the number line here, right? Now, I always like to start when I'm talking about negatives, with fractions in particular, I kind of like to start with its positive first. So if I look at positive 2/3 is here, and positive 1 is right here, obviously. Now, its direct reflection point goes on the other side. I have negative 1, and negative 2/3 falls just to the right of negative 1. Now, if I was to look at the positive side, we would say positive 1 is greater than, let me actually do an opposite because we have this set up here. So it's deleted. So if I had positive 1 and negative 2 and 2/3, so I would say this, 2/3 and 1, we would say 2/3 is less than positive 1. That's the positive side. Well, the negative side is basically the inverse of it. So we would say negative 2/3 is greater than negative 1. Why? Well, remember, negative 2/3 falls closer to 0. It's farther to the right on the number line, so it's bigger in value. Next, we had 3.5 and negative 3. So negative 3.5 is less than negative 3 here. Now, again, the reflection of this on the other side would be positive 3.5 is found here. Obviously, positive 3 is found here. So if I was looking at positive 3.5 versus positive 3, we would say positive 3.5 is greater than positive 3. The negative side is the inverse of it. Negative 3.5, its reflection point, is less than negative 3. It falls further to the right on the number line. Question number 3 then, I think is probably the trickiest of the bunch, to be honest. We have 3/7 is less than negative 3/8. So negative 3/7 is less than negative 3/8. Now again, if I look at the positive side of the number line, 3/7 falls closer to 1. 3/7. Rewrote that incorrectly. 3/8 then, very close to 3/7, falls closer to 0. Now you might be asking why. Well, whenever your denominator is smaller in number, the value is actually bigger. It's kind of weird, counterintuitive, right? Well, let's start with more recognized fractions than 7s and 8s. Let's start with 1/2 and 1/4. Which is bigger? Well, look at the overall value here. If I had a pizza and I had a big slice here versus a pizza that looked like this, which only had one slice, you can see that this half slice is bigger. There's more value to it than 1/4. So the smaller the denominator, 2 in this case, the bigger the overall fraction. So this is why 3/7, because the numerators are the same 3, the denominator shows that 3/7 is a bigger fraction. Now if I look at the negative side though, its reflection on the other side, I can see that, since 3/7 is bigger for positive, it must be smaller when it's negative. You can see that here. 3/7 falls closer to negative 1. The final question then is negative 2 is less than 16/9. So again, I like to first though, before I even look at this, 16/9 changes to 1 7/9 as a mixed fraction, right? So this is 1 7/9. So you might even change this here. Now, positive 1 7/9 falls about right here on the number line. And if I was comparing those between 1 7/9 and 2, we would say 2 is greater than 1 7/9, or 16/9, right? Well, if I go to the negative side, it's basically the inverse. -2 is less than -16/9, or less than -1 7/9, because -2 is further away from 0, farther to the right on the number line. Okay, so that ends our presentation for chapter 4.1 now in the OpenStax Pre-Algebra textbook. So I'd go ahead and get in the textbook, look at some of the questions, and see if you have any follow-up questions. Feel free to put that in the chat below, and I'm more than happy to make some additional videos if I know what questions you guys want some more of. So just to recap, our learning objectives for this class and for this textbook chapter is to understand the meaning of fractions. Fractions are a part of a whole. Model improper fractions and mixed fractions, and then convert between improper and mixed fractions, right? Or mixed numbers. So again, an improper fraction is just structured as two numbers. You have a number on top and a number on bottom, and it's bigger than 1. A mixed fraction, on the other hand, has a whole number in front of it next to a proper fraction. We then looked at equivalent fractions which have the same overall value, just could be sized up, scaled up, essentially. And then we looked at locating fractions and mixed numbers on the number line, and ordering fractions and mixed fractions on the number line as well. All right, so good luck, and I'll see you in the next video.